For centuries, science, especially physics, really operated under this beautiful, comforting myth of perfect determinism.
The clockwork universe.
Exactly. The
Yeah.
idea was so elegant, right? If you just knew the exact starting point of everything, the position, the velocity of every single particle, you could, in theory, predict the future perfectly.
It was an incredibly powerful paradigm. But it was also, as it turns out, fundamentally flawed. And over the last century or so, that certainty started to show some really deep, unsettling cracks.
Because some systems just refuse to play by the rules.
They absolutely did. Things like weather patterns, the orbits of planets, they just stubbornly resisted being described by the simple linear equations that worked so well for, a pendulum swinging back and forth.
So scientists, mathematicians, everyone had to start confronting the reality that the world is. Well, it's dynamic, it's sensitive, and it's incredibly complex.
And they uncovered this radical unifying truth. The universe is fundamentally nonlinear.
And that profound shift in thinking is exactly what we're going to get into today. This is our deep dive into nonlinear dynamics, chaos theory, and complex systems. And we're framing our understanding through the amazing work of Professor Miguel A.F. Sanjuán, whose induction into Spain's Royal Academy of Sciences really highlighted how this new way of thinking has become the essential language of all modern science.
Right. And the mission here, for you, the listener, is to see how we're breaking down these old academic wall physics over here, biology over there. We want to show how concepts like chaos and sensitive dependence and this idea of emergence, how they provide a universal framework.
A shared set of tools, almost.
A shared set of tools and insights that are now just fertilizing breakthroughs across every single one of those fields. These aren't just, some niche mathematical curiosities. They are the foundational principles that describe how the real world actually works.
Okay, let's unpack this. And we have to start right where the trouble began. With the great minds who first saw those initial tiny cracks in that deterministic universe, long before anyone even dared to use the word chaos.
So classical dynamics, the world of Newton, it was all focused on simple, clean systems, point masses, rigid bodies, celestial mechanics where everything is well-behaved and predictable.
The two-body problem is the classic example, right? A star and a planet.
Exactly. It's just a beautiful piece of mathematical elegance. It gives you a perfect, predictable ellipse. But the moment engineers and mathematicians started trying to apply these ideas to real-world messy stuff, the predictions just started to fall apart.
And these problems started showing up really early, didn't they? Especially with something like fluid dynamics. The outline mentions names like Navier, Savinol, Boussinesq. These are 19th century figures working on how water and air move.
Precisely. We know them for the famous Navier-Stokes equations that govern fluid motion, but even back then they were already deeply troubled by what they called singular solutions.
What do they mean by that?
They saw these moments in fluid motion. Think of turbulence, which is still one of the biggest unsolved problems in physics, where, and this is their incredible insight, infinitely small differences would produce enormously different effects.
Wow. So that's the first glimmer of sensitive dependence on initial conditions.
Yeah.
Decades before it had a name.
It is. They understood intuitively that the slightest change in how you started the fluid flowing could lead to a completely different pattern just moments later.
It sounds like they recognized the problem philosophically, but they just didn't have the math to really describe it yet.
That's a great way to put it. But the person who really made the philosophical pivot, the one who saw the practical death of determinism, was someone we don't usually associate with this, James Clerk Maxwell.
Right. We know him for unifying electricity and magnetism.
Of course. But his work on stability is it's shockingly prescient. In a lecture he gave at Cambridge in 1873, he laid out a definition of instability that you could literally lift and drop into a modern textbook on chaos theory.
Okay, so what was his definition?
He defined a system as unstable when an infinitely small variation in the present state may bring about a finite difference in the state of the system in a finite time.
That is the butterfly effect. That's the definition, almost 100 years before Edward Lorenz. But what did that mean for him? Did he just see it as a weird curiosity?
Not at all. Maxwell was incredibly rigorous. He drew the logical conclusion. He said, if this instability exists, it means prediction is impossible if our knowledge of the present state is only approximate and not accurate.
And here's the kicker, right? Our knowledge is always only approximate. You can't measure anything with infinite precision.
Never. So Maxwell basically recognized that true classical determinism was a fantasy, in practice. He philosophically slammed the door on the perfect clockwork universe. He didn't just notice the cracks in the foundation, he said the foundation itself was unsound and told other scientists to start studying these singularities and instabilities instead of just the simple, stable stuff.
So if Maxwell gave us the philosophical death of determinism in 1873, it really took a mathematical genius to formalize the execution.
Yes. And that brings us to Henri Poincaré and the infamous three-body problem.
Why was adding just one more body, one more planet or moon, so destructive to that mathematical certainty?
Well, the three-body problem, think of the sun, the earth, and Jupiter all pulling on each other, is so complex because the interactions are constant and they're all mutually dependent. In the two-body problem, the math just simplifies down beautifully. But with three, those simple conservation laws they break down. The system becomes what mathematicians call non-integrable.
And Poincaré was tackling this for a competition, right?
Right.
King Oscar II of Sweden wanted a proof that the solar system was stable for the long term.
He did, and in his 1889 memoir for that competition, Poincaré found the exact opposite of stability. He was studying a simplified version, the restricted three-body problem, and he dove into the incredibly complex geometry of what's called phase space.
Okay, let's pause on that. For everyone listening, what is phase space? And why was his discovery there so destructive?
Phase space is like a mathematical map where every single possible state of a system, every position and velocity is represented by a single point. And as the system evolves, that point traces a path, a trajectory on this map. What Poincaré found were these things called doubly asymptotic or homoclinic orbits.
That sounds complicated.
It is. But think of it this way. Imagine you have these boundary surfaces on your map, these mathematical tunnels that the trajectory is either pulled towards or pushed away from. In a predictable system, these tunnels are neat and orderly. Poincaré discovered that in the three-body system, the tunnel leading in and the tunnel leading out didn't just cross once. They intersected an infinite number of times.
An infinite number of times. What does that even look like?
He famously called it the chaotic tangle. If you tried to draw it, it would be this impossibly complex, self-crossing web. And that tangle is the mathematical signature of chaos. It means that any two trajectories that start infinitesimally close together inside that tangle will be stretched and folded infinitely, forcing them to diverge exponentially.
And his reaction to seeing this is legendary.
It is. He wrote, "We will be surprised by the complexity of this figure. Nothing is more appropriate to give us an idea of the complication of the three-body problem and, in general, of all the problems of dynamics." He realized this complexity wasn't a bug in his math. It was a fundamental, unavoidable feature of the laws of nature.
So that's the real birth of modern dynamical systems theory. Maxwell saw the philosophical problem, and Poincaré delivered the terrifying geometric proof that instability was baked right into the deterministic laws themselves.
Exactly. And people like George David Birkhoff followed right after, formally defining these systems and expanding on that geometric analysis. The stage was well and truly set.
So let's move from those historical roots to the formal definitions we use today. And when we talk about chaos, the absolute core concept is sensitive dependence on initial conditions, SDIC.
Right. And this is the idea that two paths that start incredibly close to one another will separate exponentially over time. And that's what makes any kind of long-term prediction fundamentally impossible.
It's the engine of chaos.
It really is. And it's a concept that feels intuitive to us, which is why the source material points out that it's popped up in literature and philosophy for centuries.
The most poetic example is that old rhyme, "For want of a nail." It's ancient, it predates calculus, a tiny failure losing a single nail from a horseshoe cascades up and up until a whole kingdom is lost.
And you see it in biology, too. Charles Darwin in The Origin of Species wrote about these tiny tipping points, saying, "A grain in the balance will determine which individuals shall live and which shall die." That single grain of an advantage is the sensitive dependence that drives evolution. The concept has always been there.
But the moment that brought this mathematical truth into the modern spotlight, the thing that really proved it, was the work of the meteorologist Edward Lorenz in 1963. This is what led to the phrase, the butterfly effect.
Lorenz's discovery is such a great story of scientific serendipity, and crucially, it came from a numerical simulation. It highlights just how essential computers are to this entire field. He was studying a really simplified model of weather, just three equations.
And the big discovery came when he was just trying to rerun a part of his simulation, right?
Yep.
He didn't start from the very beginning.
Exactly. To save time, he just typed in the initial conditions from a printout of the previous run. The original number from the computer's memory was 0.506127. He typed in the rounded value, a 0.506.
A difference of about 1 part in 10,000. That was the butterfly flapping its wings.
That was it. And at first, the two simulations, the original and the rounded one, looked basically identical. But after a simulated time of just a few months, the trajectories had diverged so completely they looked like two totally different weather systems.
It was the computational proof of Poincaré's mathematical nightmare.
It was. A system governed by perfectly deterministic laws could still be fundamentally unpredictable beyond a very short time. And it's funny, his paper was published with this incredibly dry academic title, Deterministic Non-Periodic Flow.
Not exactly a headline grabber.
Yeah.
It sounds like it took a while for the scientific world to really catch on.
It took years, partly because it was in a specialized meteorology journal, but mostly because the idea itself was just so counterintuitive. Scientists were trained to think that small changes in the input should only lead to small changes in the output. Lorenz proved that for nonlinear systems, that's just not true.
So if you can't predict the specific future path, you need a different way to analyze these systems. You need to measure how chaotic they are.
Right. And that's where we get quantitative tools like Lyapunov exponents. They're named after Alexander Lyapunov. And they measure the average rate at which two trajectories that start close together separate in that phase space we talked about.
So how do you read the result? What does the number tell you?
It's pretty straightforward. If the exponent is negative, the system is stable. The trajectories converge like a pendulum settling down. If it's zero, it's marginally stable, like a planet in a nice steady orbit. But if the largest Lyapunov exponent is positive, that's the telltale sign. The system is chaotic.
And the bigger that positive number is, the more chaotic the system.
Exactly. A large positive exponent means your predictive horizon. The window where you can make a reliable forecast shrinks incredibly fast. It's the mathematical measure of the system's baked-in unpredictability.
So we have a way to measure chaos. Now let's talk about the geometry of it. A chaotic system is non-periodic. It never repeats. But it's also bounded. It stays within a certain area of phase space. And that motion traces out an object called a strange attractor.
The concept was introduced by David Ruel and Floris Takens in 1971. An attractor is just the long-term behavior of a system. For simple systems, the attractors are simple. A fixed point if the system stops, or a limit cycle if it just repeats an orbit over and over.
But a strange attractor is...
Yeah.
Well, it's strange.
It's strange because it's geometrically a mess. It has this internal structure of infinite folding and stretching that ensures the trajectory never, ever repeats itself, even though it's trapped in this tiny, finite volume of space.
And that geometric complexity connects us directly to Benoit Mandelbrot and the idea of fractal geometry. The two concepts are really two sides of the same coin, aren't they?
They are completely intertwined. Chaotic motion creates strange attractors, and strange attractors are fractal objects. Mandelbrot's big insight was that so much of the complexity in nature, coastlines, clouds, tree branches, can't be described by simple Euclidean geometry. These things have self-similarity at different scales, and they occupy a space that needs a non-integer or fractal dimension.
A non-integer dimension is one of those things that's really hard to wrap your head around. We live in 3 dimensions. What does it mean for something to have, say, 1.26 dimensions?
It means the object is more complex and detailed than a simple one-dimensional line. But it doesn't quite fill up a two-dimensional plane. Think about the path of the Lorenz attractor. The line is infinitely long, but it never crosses itself, and it's stuck inside a finite volume. If it were truly 2D, it would eventually fill up the space like a sheet of paper.
I see. So because it folds back on itself infinitely without ever intersecting, it occupies a dimension between 2 and 3. The source material says the Lorenz attractor is about 2.06.
Right, and that fractional dimension perfectly captures its density and its irregularity. The classic mathematical examples are things like the Cantor set, which has a dimension of about 0.63, or the Koch curve at around 1.26.
And it's that self-similar fractal detail that allows the system to stay bounded but never repeat. Any little piece you zoom in on looks kind of like the whole thing.
Exactly. That continuous stretching and folding is what generates the chaos.
So we have the concept, we have geometry.
Yeah.
But the actual word chaos was officially put into the scientific literature by James A. York and his student Tien Li.
Yes. In their huge 1975 paper, Period 3 implies chaos. It was a landmark. They proved mathematically that if any system has a cycle that repeats every 3 steps, then it must also have cycles of every other possible length, including completely chaotic, non-repeating ones.
So it showed that immense complexity could come from very, very simple rules.
It was the mathematical nail in the coffin for simplicity, and it's amazing how many people were discovering this at the same time. Robert May was seeing it in ecology with period doubling. The universe was practically screaming this concept at us.
And the tool that finally let us hear that scream was the computer.
Absolutely. This entire field of complexity science is just inconceivable without computation. Poincaré and Maxwell could only theorize. Lorenz and York could actually simulate it and prove it.
And one of the most surprising early uses of that power was the Fermi Pasta Ulam Singo experiment in 1954 at Los Alamos.
The FPUT experiment, right. So Enrico Fermi was trying to use the Maniac's D computer to confirm a basic prediction of statistical physics, the idea of thermalization.
What does that mean to thermalize?
It means that energy should spread out evenly. They were simulating a simple chain of vibrating masses connected by nonlinear springs, like a model of a solid. The theory said that if you put all the energy into just one vibration mode, like plucking one string on a guitar, that energy should quickly spread out to all the other modes and become random. The system should reach thermal equilibrium.
But that's not what the computer showed them.
Not even close. After weeks of computation, which were all programmed and run by Mary Singu, the result was a total shock. The energy didn't disperse randomly. Instead, after a while, it almost perfectly returned to the single mode it started in, a phenomenon called recurrence.
So a system that was supposed to become chaotic and random didn't.
It didn't, and this was a profound challenge to the foundations of classical statistical mechanics. It was one of the first times a computer simulation revealed something so counterintuitive that it forced physicists to completely rethink their basic assumptions about randomness and order.
And that journey from Poincaré's abstract tangles to the FTUT surprise, it really represents a fundamental challenge to the whole scientific paradigm of reductionism.
It does. It's a massive philosophical shift. For centuries, physics was all about reductionism, breaking things down to find the most fundamental particle, the theory of everything. Complexity science says that the behavior of the whole system cannot be understood just by looking at its parts in isolation.
And the key philosophical statement here comes from Philip W. Anderson, the Nobel laureate, in his 1972 article, More is Different.
It's a landmark paper. His core argument was that at each level of complexity you go up, from quarks to atoms, from molecules to cells, from cells to societies, entirely new properties just emerge. And these new properties require new fundamental laws and new kinds of research.
So you can't predict consciousness just by solving the equations for all the neurons.
Exactly. The emergent properties aren't a violation of the underlying physics, but they are not strictly derivable from it. The focus has to shift from the parts to the organization of the parts.
There's a great analogy in the source material for this idea of emergence, using a series of Picasso lithographs called the Bull.
It's a perfect analogy. Picasso starts with this incredibly detailed, realistic drawing of a bull. Then, over 11 stages, he just keeps stripping away detail. He simplifies and simplifies until the final image is just a few elegant, minimal lines.
But it's still unmistakably a bull.
It captures the absolute essence of bullness. And Anderson's point is that a simplified emergent model like that can often tell you more about how nature really works than a mountain of detailed reductionist calculations. Sometimes the detail just gets in the way of seeing the bigger pattern.
And this idea was pushed even further by Robert Laughlin, another Nobel laureate, who challenged the very idea of a single theory of everything.
Laughlin argued that what we really have is a hierarchy of theories of things. The laws that govern high-level emergent phenomena like the laws of economics or the physics of a superfluid are robust and they're autonomous. They don't just reduce down to particle physics.
So it's not one single pyramid with particle physics at the bottom. It's more like a branching tree.
A constantly branching tree of complexity, yes.
And it's so important to stress again that all this uncertainty we're talking about is inherent to classical physics. It has nothing to do with quantum mechanics and the Heisenberg uncertainty principle.
That is a critical point. People often think indeterminism is purely a quantum thing, but nonlinearity brings it right into the classical world. Max Born, the Nobel laureate, asked this exact question in 1955. Is classical mechanics, in fact, deterministic?
And his conclusion?
His conclusion was no, it's not real, because Poincaré proves systems are sensitive, and Born added the physical reality. You can never measure the initial conditions with infinite precision. So, for all practical purposes, classical determinism collapses into indeterminism.
Richard Feynman agreed with that too, right?
He did. He said that already in classical mechanics, there was indeterminability from a practical point of view. Even Werner Heisenberg himself, reflecting on it later in life, said that the future of physics would depend on the progress of nonlinear mathematics. He saw that the hard, messy, real-world problems couldn't be solved with the old linear approximations.
So once the need was established, the actual field of complexity science started to come together.
It did. You had pioneers in systems thinking, like Warren Weaver. Back in 1948, he classified scientific problems into 3 types: simple problems, disorganized complexity, and organized complexity.
Disorganized complexity is like a gas in a box, where you can use statistics. But organized complexity.
That's the hard stuff. An ecosystem, a cell, an economy. It's a medium number of components with really intricate feedback loops. And Weaver knew that the old statistical tools were useless for that. He called for new methods, for computer science, and for interdisciplinary work.
And that call was answered by people like Norbert Wiener, the founder of cybernetics.
Wiener's work was absolutely fundamental because he formalized the concept of the feedback mechanism. So many nonlinear systems are complex because their output feeds back and becomes their own input, creating these self-regulating or explosive loops.
And this all eventually led to the creation of places like the Santa Fe Institute.
Yes, SFI. It was founded by scientists from all different fields, including Murray Gell-Mann, the Nobel laureate who gave us quarks. It became the central hub for this kind of boundary-crossing research because traditional university departments just weren't set up to handle it.
So we've laid the groundwork. Now let's talk about the real-world triumphs. What does this all mean in practice? It means that this new language of chaos and complexity is unlocking secrets everywhere, from the cosmos to the cell.
The applications are just incredible, and we should start where Poincaré did in celestial mechanics. We used to think of the solar system as this perfect, orderly clockwork.
But the chaotic rotation of some moons proved that was wrong. Tell us about Hyperion.
Hyperion is a moon of Saturn, and it's not round. It's shaped more like a lumpy potato. Because of that irregular shape and its elliptical orbit, the gravitational pull on it is incredibly complex. And a scientist named Jack Wisdom predicted in the 1980s that this would force it into a state of chaotic rotation.
What does chaotic rotation actually look like for a moon?
It means it tumbles unpredictably. You can't predict which way it's going to be facing. Its spin rate and its axis of rotation are constantly changing in a non-repeating way. And this prediction was confirmed spectacularly when the Cassini spacecraft got to Saturn in 2005. The data was a perfect match for Wisdom's chaotic model.
So there's deep unpredictability even in our own solar system. And it's not just Hyperion.
Nope. Pluto's moons Nix and Hydra do the same thing, and this scales all the way up. Cosmological models are now incorporating these ideas. There's a chaotic universe model that looks at the nonlinear interactions between dark energy, dark matter, and radiation.
And what did it find?
It found evidence of a strange attractor governing how these cosmic components evolve over time. This suggests that the history and future of the entire universe might be subject to these chaotic dynamics.
Bringing it back down to Earth, chaos theory has been huge for geology, right? For understanding things that seem random but aren't.
The reversals of the Earth's magnetic field are a perfect example. They happen at irregular intervals over thousands of years, and they look completely random. But the process is driven by the turbulent, nonlinear flow of liquid iron in the Earth's core. And simple chaotic models, like the Rickettake 2-disk dynamo, can successfully reproduce that same irregular, random-looking pattern of flips.
So it's not random noise. It's the signature of a deterministic but chaotic system.
Precisely, and that distinction is everything. We see the same thing in the study of slow earthquakes on the Cascadia subduction zone, that massive fault line off the Pacific Northwest.
What do you find there?
By analyzing the history of these slow slip events, researchers found the dynamics weren't random, but showed signs of low-dimensional chaos. They could actually reconstruct the strange attractor for the fault's behavior.
And could they use that to predict the next slip?
Well, yes and no. They could estimate the predictability horizon, the window of time before the chaos takes over, and it turned out to be incredibly short.
How short?
Just days to weeks. And that is a profound result. It means that even if we had a perfect measurement technology, the inherent nature of the system itself limits our ability to make a long-term forecast.
Now let's pivot to the life sciences, where complexity is just everywhere. You have the Hodgkin-Huxley model from the 50s for how nerves fire.
Right, a Nobel-winning model that used differential equations to describe a biological process. And that was later simplified into the Fitzhugh-Nagumo model, which actually borrowed ideas from the Van de Poel oscillator, an old nonlinear circuit used to model the electrical activity of the heart.
So a direct line from engineering chaos to fundamental biology. And this led to the revolutionary idea of dynamical diseases.
This is the idea from people like Milton and Jung that many diseases aren't just a broken part. They're a problem with the system's rhythm, an abnormal temporal organization.
Epilepsy is the classic example of this, isn't it?
It's the most vivid one. A healthy brain's EEG recording is actually very complex. It looks chaotic. That complexity represents the brain's flexibility. But during an epileptic seizure, the EEG changes dramatically. The activity becomes highly regular, periodic, and organized. It collapses onto a simple pathological attractor.
So the disease is actually a loss of complexity. The brain gets stuck in a simple, repetitive loop.
Exactly. The healthy state is chaotic, the diseased state is orderly, and this applies to things like cardiac arrhythmias and other conditions too. It's a completely different way of thinking about pathology.
And now we're not just analyzing complexity in biology, we're actively engineering it in synthetic biology.
Yes. Using the principles of nonlinear feedback to design life. There were two landmark papers in Nature back in 2000. One group built a genetic toggle switch in bacteria, a circuit that could flip between two stable states.
And the other.
The other group built the repressilator, a synthetic genetic clock that produced rhythmic oscillating proteins. And they did this by modeling the genes and proteins as systems of nonlinear equations. They were using the tools of chaos theory to build predictable, dynamic behaviors into living cells.
And finally, a really powerful modern example of sensitive dependence. The antlion paradox study from 2024.
This study from the African savanna is just a perfect illustration of the butterfly effect in ecology. It's all about the connections between acacia trees, ants, and lions.
So what was the initial stable state?
The acacia trees had this great deal with a certain species of ant. The ants lived on the trees, and in return, they would attack elephants and other herbivores that tried to eat the tree.
Okay, a nice stable mutualism. So what was the tiny perturbation?
An invasive species of large-headed ants moved in. They were more aggressive. They kicked out the helpful ants, but they weren't any good at defending the trees.
And that one small change in the ant population
Caused a massive cascade. Without their ant bodyguards, the elephants started eating the acacias, which reduced the tree canopy. The change in vegetation altered the landscape, which changed the behavior of the lion's prey. Zebras, who like open plains, became less common. Buffalo, who like denser scrub, became more common.
And so the lions.
The lions switched their primary food source from zebras to buffaloes. A change in an ant species ultimately dictated what the apex predator was eating. That is sensitive dependence on a massive ecosystem-wide scale.
That's incredible. So it's clear these ideas are powerful unifiers.
Yeah.
And yet there are still huge barriers to this kind of thinking in the academic world.
The challenges are really structural. The source material points out the biggest one is just the language barrier between different fields.
You'd think math would be universal.
The math is, but the jargon isn't. The same exact mathematical event, say, a bifurcation where a system's behavior suddenly splits, might be called a critical transition by an ecologist, a phase change by a physicist, and a limit cycle instability by an engineer. They're all talking about the same thing but using different words.
And that's all reinforced by how universities are structured, right? The funding, the departments, they're all these rigid silos.
Absolutely. If you're a complexity researcher, you have to try and fit your grant proposal into a physics box or a biology box, even though your work lives in the space between them. The system actively discourages the very kind of integrative research that complexity science is all about.
So how do we train the next generation of scientists for this nonlinear world without just creating people who know a tiny bit about 10 different fields?
The consensus seems to be that you still need a firm anchor in one discipline. You have to master physics or math or biology first to ensure you have rigor. But at the same time, the training has to shift away from simple, linear, closed system models and teach students to see the nonlinearity and the feedback loops that are everywhere.
It's a shift in mindset, really.
Yeah.
The source mentions the philosophy of James A. York, the guy who coined chaos.
Right. York's view is perfect for this. He said, "The most successful people are those who are good at Plan B." Research isn't about just banging your head against one problem. It's about being flexible, changing your question and your approach until you find a fit. He said a math degree is a license to explore the universe, and that captures the spirit of it.
And Freeman Dyson gave us that wonderful allegory of the two types of mindsets needed for this, the birds and the frogs.
It's such a great way to think about it. The birds are the big picture thinkers. They fly high and look for the grand unifying concepts that connect everything, like the idea of the strange attractor itself.
And the frogs.
The frogs live down in the mud. They love the details. They solve specific, concrete problems one at a time. And Dyson's point is that you need both. You need the visionaries, and you need the meticulous researchers who are actually applying these models to the fault lines and the ant colonies.
It really feels like the greatest minds saw that complexity wasn't a mistake or a failure of the math. It was a fundamental truth, just waiting for us to find the right tools and the right mindset.
Yes. Gerd Binnig, who co-invented the scanning tunneling microscope, said it perfectly. He said he was convinced that investigating chaos would produce a revolution in science similar to what quantum mechanics did. And that's a huge statement, putting it on that same top tier of scientific revolutions.
So if we pull this all together, our journey today shows that the core takeaway from nonlinear dynamics is that prediction is fundamentally limited, even in deterministic systems. And that forced science to pivot away from pure reductionism and toward a focus on emergence, on the patterns and collective behaviors that arise from complex interactions.
And this new framework has built bridges between fields that used to be totally isolated. Whether you're modeling a moon's rotation, designing a genetic circuit, or analyzing a fault line, you're using the same core language of attractors and bifurcations. And that makes understanding complexity more than just an academic exercise. It's a critical tool for the future, for tackling challenges like climate instability, AI safety, and bioengineering.
Understanding complexity really means seeing the world not as a collection of separate pieces, but as one vast, interconnected, adaptive system where a tiny push in the right or wrong place can have enormous consequences.
Which brings us to a final provocative thought for you to consider, building on the work of Yuri Alon in systems medicine. If we can start creating a periodic table of diseases, organizing them not by the organ they affect, but by the shared nonlinear dynamics of the system's failure, what else could we recategorize this way?
What if we created a taxonomy based purely on dynamic behavior?
Exactly. Could we classify different kinds of financial crises or social network collapses or geological instabilities not by their physical parts, but by the chaotic or oscillatory patterns they all share? So we encourage you to look at your own field, your own work, your own life, and ask what it looks like through this transformative lens of chaos.